I accidentally mute myself. Okay, so we were talking about simple isothermal calculation, and we studied or saw here the different oxidation states that the system was taking into account when doing calculations. And we put 1 mole of this elemental iron in sodium chloride. We realized that there were no changes in the oxidation states. How do we incorporate them is what we are going to learn next. Another thing I want to show, when we customized the table, we also added some activity and fugacity coefficients, and you'll see that the software will show those values here. So again, you can always modify or reduce, increase this table to show the data or information that you want to see. Whenever you want to share these results to someone that doesn't have the software, access to the software, but you want to share the results, you can always export this table or this report, and the software will calculate or will create a comma-separated text file or a CSV file. You simply name it, and then it will create a report for you. Okay. Well, I put a corrosion rates, but it's really no corrosion rates. And then you'll go to your location and you'll see that now you have an Excel spreadsheet with the information that you created or the software gave you regarding the calculation. It's something that I like to show because, again, if you want to share that information with someone, you can simply export this easily. Okay? Okay, that is one thing. Now let's go back. Now we are going to repeat the same calculation. Okay, I want to repeat the same calculation, but there is something that I want to talk about, and that is the redox reaction. Okay, let me go back here. So when we are talking about redox reactions, we already saw all of this here. When we are talking about redox reactions, it is important that we take them into account because they become really important when you're working with corrosion. So if you are studying corrosion rates, you need redox on. If you're doing, and because you calculate corrosion rates, you will be also seeing polarization curves, and those are important, and it is important to have the redox reaction on. Or if you are also working with pore-based diagrams, stability diagrams, you need to specify specific oxidation states. So we all know that these half reactions are, or these redox reactions are also known as half reactions. And this is a type of chemical reactions that involve electrons. That's what makes them different, right? So you will have one species that is going to be oxidized, and another species that is going to be reduced. So this is a simple example of iron in an oxygen-free environment here. So you will see that iron is the one that is oxidizing because its charge is changing from 0 to a +2, and it's producing 2 electrons, and you need a reduction reaction to take those electrons. So this H+ from solution goes from +1, and it makes hydrogen bubbles to produce this hydrogen 0, and so that means that we are reducing the charge of this H+. And we have gained electrons in this reaction. So this is the net reaction that is happening. And this is what we probably are expecting to see in our calculation if we turn on the redox reaction in the calculation. And how do we do that? We simply go to the menu bar, to the tools bar, and turn on the redox reaction. So let's go back. And we have two options. We can either right-click on this, copy, and create a new calculation, paste. Oops, sorry, I should have not done that. I have to paste it on the stream. So again, right-click on the sub-calculation, copy, click on the isothermal calculation stream, right-click on it, and paste. That will create a new single point calculation or isothermal calculation. We're going to rename it, and we are going to say that the redox button is on. Redox. Okay. We make sure that our redox is on. We go here, redox. You also see that in the summary section, you have the redox selected. There's a way to find out what if your redox is on or off. Another thing that I like to show is you'll see that next to the redox button, you'll see drop-down arrow. And what the software does is that it basically surveys the system, and it realizes that you have chlorides in the system, that you have sodium in the system, and that you have transition element in your system, iron. Okay, so when you turn this redox on, immediately the software knows that you're talking about metal, and it turns on the iron oxidation state. Okay, so that is selected. Now, if you were to have another species that you know that changes the oxidation state, like sulfur, for example, so you will need to go and define that sulfur as well. But that will be our next example. For now, let's just recalculate. Just click on the calculate button here. And calculation is completed. You'll see that there is a check mark. You go to the report. And same idea here. So we haven't changed. Everything should have remained the same. Let me see. Yeah, even with the activities and the K values, because we copied the previous calculation. Okay, so you'll see now that there are differences here. The pH now is no longer 7. You see an increase in pH. Okay, so from 7 to 9. What else do you see here? You start seeing that now you start producing something called magnetite. That is what is going to precipitate out iron oxide. This is the good protective layer that reduces corrosion rates. Okay. You now see the species output table is much, much bigger and longer than the one that we had before without the redox. In here, the software is calculating the distribution of water, the distribution of course, how the sodium and chloride split in water, right? It goes all to water. And now we are saying, or the software is saying that 0.33 moles of this iron or of this magnetite is being formed and is in the solid phase, right? And you will see some other species here. These values down here that you see that are so low, probably you can always I think that you can customize them. I'm not positive, but I think in some cases you can reduce the amount of species depending upon, like, if this is too low, you can just ignore the species. But what I want to show you here is this elemental distribution. So now we don't have any iron plus, any iron, elemental iron. It's no longer in zeros. The element is no longer there. Sorry. What you're producing now is iron plus 2, 0.33 moles, and iron plus 3. Those That's the distribution of the species. Okay, so Mariana and Joaquin, this is also this type of calculation is always a good idea to do, to see which layers you're forming and how much of it is forming in the system. I always like, if I'm doing a Pore diagram, I always like to complement it with this type of study, the single point type of study, because it will let you know which layers you're producing. Okay. So that is the redox for the iron. So now we are taking into account another thing that you will see that is calculated is the oxidation reduction potential. That is another value. Now let's imagine that, yes, Pradeep? You have a question?
Diana,
yeah.
Diana, I see you changed the framework to MSc. So
yeah, we started with the MSc.
MSc? Okay.
Yeah, all of this we have done it with the MSc from, yeah, we left the default.
Okay, sure. Thanks.
Yeah. Now let's say that you have the sodium chloride, iron in sodium chloride, you have the redox, and now you also want to include sulfur in the system. Somehow, maybe you have H2S and it dissolves in the system. So what I'm going to do is to do a third calculation and see how we can explore those options. So right click on the sodium chloride redox, and we are going to copy it under the isothermal calculation. Paste. Let's rename it, and I'm going to put H2S in the system, right? So we go to this sub-calculation, and what I want to add here is a molecule, 1 mole of H2S. I type H2S, I add 1 mole. I make sure that my redox is on. So I'm going to turn on my redox. And also, I'm going to make sure that I have selected, this redox has selected the iron in this drop-down arrow. But now, this is what I was saying. Now the system knows that you have a sulfur species. You have added a sulfur species. And the software knows that it's not a transition metal. Only the transition metals are turned on by default. Only the transition metals are turned on by default. This is non-transition metal, so it doesn't turn it on, but we know that there will be oxidation states in the sulfur. Okay, so for now, we are not going to turn on redox for sulfur. What we are going to do is we are going to do a calculation, but the software is going to assume that the oxidation state of sulfur stays as -2, because that's the oxidation state that we have in this molecule, -2. Calculate, and then we go to the report. The pH is not as high as before, maybe because we added that H2S and now it speciated and increased our hydrogen ions in solution. This is now the solids that are being formed. Pyrrhotite, iron sulfide. Iron sulfide is the solid, is the main layer that is being predicted to be formed. And in the element balance, you will see that you don't have elemental sulfur left. And the most, if not all, the iron +2 went into pyrrhotite. Iron +2. Okay? So notice that for the sulfur, like I was saying before, the sulfur the sulfur has only one oxidation state of -2. Now, what if you want to include some other oxidation states of sulfur? You probably think that you are having some reduction of this oxidation state. Maybe you also have elemental sulfur in the system. Okay. So there are two ways to do it. I'm going to show you the long way because I feel like it's the one that gives you the most options. You go to chemistry, make sure that you are here in this calculation. Go to chemistry, model options. And you'll see that it opens a new window where you will have access to the data banks. Yes, we have selected the MSc. Then you have redox. We know that we turn on the redox for iron. And we have three different oxidation states, elemental, +2 and +3, ferrous and ferric. We also have sulfur in the system. We can expand it. So we have way many more oxidation states. And maybe we want to just understand if we will have -2, 0, which are the default, right? We had -2, the default. Maybe we go to elemental sulfur. Maybe we will have in +2 and +4. I don't know, but you have these options here to include them in the calculation. And then you click OK. So you need to recalculate. You can either press your F9 key to recalculate, or you go back to the definition tab, calculate. Of course, we are adding more calculations. It will take a little longer. We go back to our true species. Pyrrhotite is still the iron sulfide is still the solid phase that forms. And now you'll see that the software is adding, it's not only including the -2 oxidation state, it's also including the +2, which is virtually nothing. And it's also including the +4, virtually nothing, and the elemental sulfur. Okay. But again, in this case, it didn't matter that we included these oxidation states. It just didn't matter. And in some cases, where you know that you have those oxidation state changes, it is important to see what is the effect of those in this type of calculations. And that's how you do it, using the chemistry model. Okay? Okay, so that is isothermal calculations, no redox, redox on, and including some other redox reactions that are not part of an elemental or a transition metal. Are there any questions? The reason why I spend so much time here is because this is important when you go now to the 4-bay diagrams, where it's all about the redox reactions or half reactions. Any questions at the moment?